Now, in the case of motion of charge in a magnetic field, the magnetic force is perpendicular to velocity of the particle. So, no work is done and no change in magnitude of velocity is produced. See, F equals to Q V cross B. Displacement and force are perpendicular direction and hence no work is done. If m is the mass of a particle which is moving with velocity v in a circle of radius r, then there exists a centripetal force Fc equals to mv square by r, where v is the velocity perpendicular to magnetic field. Then F equals to qvb equals to mv square by r. If the velocity v is perpendicular to magnetic field, the magnetic force is perpendicular to both v and b and will balance the centripetal force. Magnitude of magnetic force is qvb. Equating both forces, we get qvb equals to mv square by r. Then r equals to mv upon qv, where mv is the momentum of charge. The larger the momentum, larger is the radius and bigger the circle described. If omega is the angular velocity, then omega equals to v by r. Omega equals to qb by m. Also, omega equals to 2 pi mu. Equating both, we get 2 pi mu equals to qb by m. Then mu equals to qb upon 2 pi m. Time taken in one rotation equals to 1 by frequency. Then time taken t equals to 2 pi m upon qb. If the velocity has component parallel to magnetic field, it will make sure that parallel movement along the field and the path of the charge would be helical. The distance moved along the magnetic field in one rotation is called pitch, P. Using equation omega equals to 2 pi mu equals to qb by m, we have P equals to Vx into T equals to 2 pi m Vx upon qb, where Vx is the velocity component of charge along the magnetic field and it is denoted by Vh. The particle has tendency to perform a circular motion in a plane perpendicular to magnetic field. The resulting trajectory will be helix along the magnetic field line.